In this video, we're going to learn how to solve a system of three equations with three variables using the elimination method. So just to start off, to keep myself organized, I'm going to number my equations. And the goal of elimination is to take any two of your equations, let's say 1 and 3, and be able to add them in some way such that one of the variables cancels out. So what we're going to do is we're going to take one pair of equations, cancel a variable, then take a different pair of equations and cancel that same variable and solve the resulting system of equations. So let's take a look at 1 and 3. 4xy plus 2y plus z equals 1, and 4x minus 2y plus z equals 3. I notice right off the bat that if I just add those two equations, I would get my y terms to cancel. So I'm going to choose to cancel my y variable here. It does not matter which variable you cancel, as long as you're consistent in both your first two steps. So I'm going to take that first equation, and I'm going to add it to my second equation. So when I add those two equations, 4x plus 4x is 8x. 2y minus 2y, well, the whole idea of elimination is to get a variable to cancel. So the y's go away, z plus z is 2z, and 1 plus 3 is 4. So I'm going to call this equation, let's say, A, just to keep myself organized. So I picked equations 1 and 3 to start off with. I'm going to pick a different pair, and it doesn't matter which pair as long as it's not 1 and 3. Let's say 1 and 2. That's the pair I'll work with now. And I'm going to cancel the y's again. However, if I'm looking at equation 2, let's say I've got 4x plus 2y plus z equals 1, and x minus y plus z equals 4, I notice if I were to add these, my y terms don't cancel yet. But if I did have a negative 2 in front of that y, then when I added it to 2y, I would have them cancel. So all I'm going to do is I'm going to multiply that second equation by 2. That way I would have a negative 2 out in front of my negative y. So when I multiply this 2 into my equation, I end up with 2x minus 2y plus 2z equals 4 times 2 is 8. I'm going to do the same thing where I add those equations now. So I'm taking equation 1 and a modified version of equation 2, and I'm adding them. 4x plus 2x is 6x, minus 2y and positive 2y makes 0. Again, the whole idea was to eliminate the y here. 1z plus 2z is 3z, and 1 plus 8 is 9. And let's call this equation B. Now, your resulting equations should no longer have a y with them. So if I take a look at what I have here, my equation A that we solved for first, and my equation B that we solved for after that, this is just a system of two equations in two variables. This is exactly the same as the older elimination method that we did, where we maybe multiply both equations by something, try to get one of the variables to cancel, and solve from there. So again, it doesn't matter which variable you choose to cancel. It looks to me like the z's might be a little bit easier. If I'm looking at 2 and 3, well, if I multiply the top equation by 3, I would get 6z, and if I multiply the bottom equation by negative 2, I would get a negative 6 as a coefficient for that z, and when I add these two equations, then they would cancel. So what I'm left with here, 3 times 8 is 24, 3 times 2 is 6, and 3 times 4 is 12. Negative 2 times 6 would get me a negative 12x minus 6z equals negative 18. And now, when I add these equations, 24x minus 12x is positive 12x. And again, the whole idea was to eliminate those z's, so it makes sense that those cancel. And 12 plus a negative 18 gets me negative 6. When I multiply, or when I divide out that 12 on both sides, I'm just left with x equals negative 6 over 12, or negative 1/2. So that's the first variable we solved for. Remember when we started though, we did have 3 variables. So now that I have one of those variables solved for, I'm going to take that value and plug it back in to one of my equations in my previous step. Now the reason I don't go back to the beginning and plug into one of those equations is because if I plugged in for an x, I would still have 2 variables y and z that I wouldn't be able to solve for. However, if I take one of my other equations, let's say I plug into equation b, which was 6x plus 3z equals 9, when I plug in that negative 1/2 for x, the only variable I have left to solve for here is z. 6 times negative 1/2 is negative 3, plus 3z equals 9. If I add 3 to both sides, I'm left with 3z equals 12, and when I divide out that 3, I'm left with z equals 4. Alright, so I have an x equals, I have a z equals, the only variable I'm missing is y. So now I'm going to go back to one of my original equations, and it doesn't matter which one, all 3 of them will work. I'm going to just pick equation 1, and I'm going to substitute in my x and my z values so that I could solve for y. So 4 times negative 1/2 plus 2 times y, that's what I'm looking for, plus 4 equals 1. 4 times negative 1/2 is negative 2. And if I simplify a little bit further, I have 2y plus 2 equals 1 if I combine the negative 2 with the positive 4. And if I subtract 2 on both sides, I get 2y equals 1, negative 1 when I subtract 2. And when I divide out the 2, I get that y is also negative 1/2. So just to collect my work, you could see your answers one of 2 different ways. So notice how much work we have here for this one problem. Generally, there is a lot of arithmetic for these problems. They are not conceptually hard. The problem is that you're doing so many different multiplications and additions is that it's so easy to make a sign error somewhere so that when you get one of your answers, you're getting a weird looking decimal that you have an idea of is not right, but you can't trace your work back to where it went wrong. So always just start at your first step and make sure you multiplied everything out correctly, all of your signs are correct, because that is where the difficulty comes with these problems. So you might see your answer written like this with your x, y, and z boxed, or you might see it as an ordered triple instead of an ordered pair now because there are 3 variables. So my x is negative 1/2, my y is negative 1/2, and my z is 4. So you might also see your answer written like this. Of course, you can always check your answer just by substituting in that x, y, and z value for each of those equations just to make sure it works. That's how you'll know for each of these 3x3 systems that you got it correct. Now I'm going to do one more example, but I encourage you to try this one on your own and see how you fare. Check your work once you've finished. So I'm going to do the same strategy. If I'm looking at my x's, y's, and z's, and I'm picking one of them to cancel, I notice again that I wouldn't have to do anything to both these equations to get my y's to cancel. So I'm going to start by adding equations 2 and 3. And when I add those, something interesting happens in this case, because I'm noticing that my coefficients for my y's will cancel, but it is also the case that my coefficients for my z's, my x's will cancel. So when I add those, negative 3x plus 3x is 0x, negative 2y plus 2y is 0, and z plus 3z is 4z. Negative 21 minus 9 is just 12. So when I solve for z here, I end up getting z equals 3. Now notice in this case we actually didn't have to go through a second set of systems to solve for one variable, because two variables cancel to begin with. So now that you know z, you could plug back into all of these equations and eliminate the z entirely from it. So all I did here was substitute z back into each of my original equations and then rearranged it so that let's say I moved the 3 times 3, which is 9, over to the other side, so that they were all equations with just two variables. So now that I have just equations in two variables, this becomes the same problem as a 2 by 2 system of equations for elimination. Pick any two equations. I'm going to pick my top two in this case, and solve them by elimination. Alright, so as I'm looking at this, I'll finish this one off just so you have an idea of what your answer should be. If I add these equations, nothing cancels yet, but let's say I'm trying to get my x's to cancel. If I had, let's say, a negative 6x as a coefficient here, and then if I multiply the second equation by negative 2, I'd have a positive 6x as a coefficient, and I would get those to cancel when I add them. So when I distribute that out, my first equation is negative 6x plus 3y equals 33. And my second equation is a negative times a negative, remember, is positive. Negative 2 times 2y is negative 4y. And negative 2 times 18 is negative 36. So now when I add those equations, my x's cancel. 3y minus 4y is negative 1y equals negative 3. If I divide out that negative 1, I find that y equals just 3. So again, now I have a z value, I have a y value. I'm going to plug back into pretty much any of these equations because I already have two of my variables solved for. I'm going to pick this equation right here just because there's only two variables there. So when I plug back into that, negative 3x is what I'm looking for, plus 2 times 3 equals 18. Negative 3x plus 6 equals 18. When I subtract 6 on both sides, I'm left with negative 3x equals 12. And when I divide out that 3, 12 divided by negative 3 is negative 4. Again, for each of these, once you have your three solutions, just plug them back into each of your original equations to make sure you didn't make any arithmetic errors. So I'm going to write my answer as an ordered triple and call it a day. So the reason this problem was a little bit less work is because when I added equations 2 and 3 to start off with, I had two variables to cancel. That generally won't happen, but I wanted to show you the special case here of when it does happen. More generally, you want to be thinking about the first example that we did, where you take two equations, add them, get a new equation. Take different two equations, add them to cancel the same variable that you canceled in the first one to get another equation. Then solve that system of equation and start plugging back into each of your equations.